The mid-50s, a time of exuberant change. From the Depression of the 30s, the nation had plunged into the strictures and rationing of World War II. Now, for the first time in decades, Americans were enjoying a booming economy, and they ate it up. The jet age had arrived, and Americans were fascinated with the sleek new swept-wing fighters that had cleared the skies in Korea and broken the sound barrier in level flight. Our great national icon, the automobile, reflected their style. It was the era of poodle skirts, hula hoops, and hydrogen bombs. Behind the fads and conspicuous consumption, perhaps fueling them, lay a dark specter. Our World War II ally, the Soviet Union, was now an implacable enemy, and they had the bomb. The space race was on. The US and Soviet Union were developing missiles to deliver nuclear warheads and to place payloads in orbit. The Soviets were ahead at the first lap. Sputnik, barely the size of a soccer ball, carried only a simple transmitter, but its monotonous beep sent a chilling message. Soviet test sites lay deep in a gigantic and seemingly impenetrable landmass. The US was desperate for intelligence on these threats. A gawky, highly specialized U-2 could overfly the sites at 80,000 feet, but its slow speed and agonizingly long loiter time made it increasingly vulnerable to improving Soviet air defenses. It was only a matter of time. The US government needed a better reconnaissance platform. By 1956, Lockheed was designing such an aircraft, the CL-400. Pratt Whitney was selected to develop a radical new engine, the liquid hydrogen-powered 304. This highly classified project was codenamed Suntan. At the same time, the U.S. Navy was formulating an advanced attack plane, the Mach 3 dash capability. It demanded an engine with far more thrust than any yet existing. Pratt & Whitney was approached to create a powerful new turbojet, the J58. Dick Core was chosen as chief engineer for both projects.
Suntan was a project to develop a hydrogen-fueled fan for very high-altitude operation, about Mach 2 at 100,000 feet. And the engine was a concept invented by a fellow by the name of Ray, I think that was R-A-E. And he convinced the Air Force that this was the right kind of engine to use at very high altitude. But he had no facilities for developing an engine, and the Air Force turned to Pratt & Whitney to develop this engine, which we call the 304. And at the same time, we had another project. I was assigned another project, which was the J58 for the Navy. And the Navy at that time was very interested in using what's fuels that were doctored with boron.
Development of these new engines began in East Hartford, but it quickly became apparent that the Connecticut facility possessed neither the space, the noise containment, nor the security to see the programs through. The search for a new site led to a tract of land in the northeastern part of Florida's Everglades. The remote location near West Palm Beach was ideal, except for swamps, mosquitoes, alligators, and rattlesnakes. In 1957, a contract was signed for construction of the new facility, and Pratt & Whitney's Florida Research and Development Center was born. Initial development was daunting. There was no direct access to the 7,000-acre site. The state of Florida agreed to build a road, the Beeline Highway. But the segment from West Palm Beach to the plant was delayed when the Loxahatchee Slough refused to cooperate. It swallowed tons of fill and 2 bulldozers. Designer Ray Schneider was one of the first employees hired specifically for the new facility.
Well, the first 6 weeks I was down here, the Beeline Highway wasn't open because of a quicksand problem, and they couldn't build a section of the road. So they routed us through the swamp on a dirt road, and it was very interesting because it was hard to have 2 cars pass at the time. The road was so narrow.
After more tons of fill and months of work, the Beeline was finally completed. Plant construction was nearly as difficult. Unusually rainy weather turned construction sites into a sea of mud. Fill for building sites came from borrow pits, adding numerous new ponds and lakes. Environmental concerns led to creating new wetlands to replace those being filled for construction. Charles Rolke, the first general manager of the new facility, faced a number of obstacles. Pratt Whitney was unwilling to part with experienced support personnel from Connecticut, and much of the workforce had to be recruited and trained locally. At the same time, the customers wanted work on the 304 and J58 to progress as quickly as possible. Construction was barely underway when J58 and 304 engines began arriving from East Hartford. Work on these projects advanced rapidly in makeshift rented shops. First permanent structures completed were the test stands. The Air Force built 2 facilities to generate liquid hydrogen for the 304. They were codenamed Mama Bear and Papa Bear, and for security reasons they were given a cover story. Local residents were told they were processing plants for the Apex Fertilizer Company. Despite the primitive conditions, spirits were high. A young engineer, Frank Maccabee, was part of that original cadre.
A group of us, about 30 or 40 engineers and their families, had been transferred down from Hartford. All of us were young. The test engineer group, of course, we had a management team as well. But our families were young. This was an area that had not been developed at all. The communities were practically bare of houses. As a matter of fact, a whole new community was built in Lake Park, where I live, and we were one of the first families to move in there. Everything was new, including the technology, the challenge, the relationship with the customer, the facility itself. It was all very exciting, and we were all eager and didn't know that we couldn't do some of the things that actually were accomplished, and we just had a lot of fun. There was a tremendous camaraderie.
A year before the main office building was complete, both engines were ready for testing. In September 1957, the primitive quiet of the swamp was shattered by the roar of the first 304 test run. A thunder heard for miles under sunny Florida skies. The J58 too progressed well for the Navy, and the engine made its initial test firing on Christmas Eve, 1957. On May 27, 1958, the Florida Research and Development Center was officially dedicated. The new Florida Facilities direction may have seemed clearly defined. The nation's was not. Within the next 5 years, we saw the election and endured the assassination of a young new president, watched the communist takeover of Cuba, and sweated through the ensuing missile crisis. We held our breath as tiny Friendship 7 carried 41-year-old John Glenn into history as the first American in orbit. We watched the slow expansion of American involvement in a remote Asian country, and honored the call to place a man on the moon by the end of the decade. Pratt & Whitney faced its own unique challenges. In the early stages of the 304 program, skeptics feared that liquid hydrogen would never be safe. The mere mention of it conjured up visions of the Hindenburg disaster. But Pratt & Whitney devised efficient new ways to handle this volatile fuel, and the 304 proved safe and successful. Both programs were progressing on schedule. Then came a strange musical chairs change. The Navy lost interest in developing their Mach 3 attack plane, and work on the powerful J58 ground to a halt after just a few test firings. At the same time, things were going badly for the Air Force's CL-400 program. As designed, the aircraft presented support problems, was based on technology already becoming obsolete, and could not carry sufficient fuel for the needed range. The Air Force decided to start with a clean slate and canceled development of the CL-400. Work on the 304 hydrogen engine was suspended. The setback was brief. Pratt & Whitney's new expertise and new facility were just beginning to blossom. The U.S. still required a long-range reconnaissance platform. The Air Force and CIA recruited legendary aircraft designer Kelly Johnson and the super-secret Lockheed Skunk Works to design a new plane, the A-11. To meet the demands of high-altitude Mach 3 flight, they turned to Pratt Whitney's new J58 as the most promising engine candidate. At the same time, the need for space launch capabilities was growing rapidly. The Air Force enlisted Pratt & Whitney's newfound expertise with liquid hydrogen to develop a compact, powerful upper-stage booster engine, the LR-115. In 1961, the program was transferred to NASA, and the engine became known as the RL-10. The last contractual 304 tests were still underway when RL-10 development began. The company never missed a beat.
I had the good fortune of being the test engineer responsible for assembling and testing the first RL-10, which we called FX-121. It was a new technology. Hydrogen and oxygen had never been used as a rocket fuel before in any quantity. The cycle that the engine was based on was new, the bootstrap cycle. The materials that we used were used for the first time in this environment. It was just all new and exciting. I remember the first time we fired the RL-10 was on third shift. It was the middle of the night in the swamp. It was black as ink, a starry sky, and when that engine lit off, it was like doomsday had arrived. A tremendous sheet of flame out the diffuser, a noise that you just never heard before. At least I hadn't. It would actually get into your lungs and breathe for you. It was just tremendously exciting. And the engine ran and ran and ran and ran. As a matter of fact, I believe it was 426 seconds, which doesn't sound like long, but at that time it was the longest duration firing of any rocket engine anywhere. We had set a new record that night.
While things went well for the new RL-10, adapting the J58 for the A-11 was not as simple as anticipated. The technical demands of sustained Mach 3 flight were daunting. They required not just new designs, but completely new concepts. A brilliant engineer, Bob Abernathy, devised ducts that allowed inlet air to bypass the compressor in supersonic flight. This simplified the inlet design, and at high Mach numbers, virtually converted the engine from a turbojet to a ramjet.
The engine structure had to stand these very high pressures at 1,500 degrees Fahrenheit, bottle temperature. That melts most things. The lab found a way to make it possible to weld what we used to use for turbine blades called lost boy in sheet structure.
If the J58 had to operate at temperatures beyond the tolerance of available metals, there was a simple solution: do the impossible and create new ways to process previously unusable alloys that could do the job. Joe Moore was a young materials engineer when he was faced with these challenges. Considering the complexity of the task, his first exposure to the materials laboratory was disconcerting.
Well, shortly after I came to work, I looked at the situation. I thought, my God, we're not a development lab, and that was why I'd been brought there. However, the guy that brought me said he wanted to make it more of a real development laboratory, and I looked at it, and then I thought, my gosh, this place is just a control lab. They check pieces that come in and raw stock that comes in to see if they meet the mechanical and chemical requirements, and that's about it. And so I truly did this. It sounds corny, but I made up my mind that I wanted to see us become the best laboratory in the world.
Design of the A-11 at Lockheed faced similar challenges. At Mach 3, portions of the aircraft skin would reach temperatures of nearly 1,000 degrees, well above the melting point of conventional materials. Kelly Johnson's engineers turned to Pratt & Whitney's pioneering work with titanium alloys for the answer. The next few years of RL-10 and J58 development were fraught with difficulties as FRDC delved into the unknown. Dick Mulready was a driving force behind the new science of cryogenic fuels.
Hydrogen is an excellent working fluid, which means that it doesn't take much of it as a flow material through a turbine to generate a lot of power. And because it was hydrogen, we could take the hydrogen that was going to be burned in the cool thrust chamber, and the heat that it extracted from the thrust chamber was enough to drive the turbopumps. So the hydrogen flows through the pump, around through the cooling jacket, and then up into the chamber. So all of it is used, nothing is wasted, there's no gas generator that throws away anything. And so it's an elegant sight. It really is perfection. And it's the reason the engine has now lasted over 40 years. It's the longest living mark Pratt Whitney for an engine. Well, we took the engine, which had been run horizontally, put it in a pair up in the E5 stand, and made a firing one day. Al Gardner was with me. He was the Air Force project officer, and everything worked fine. The next day, there was a second firing on the E5 stand, and there was an explosion.
That second firing was eagerly attended by a group of NASA officials, led by the renowned German rocket scientist Wernher von Braun. William Missimer was a young instrumentation engineer who witnessed the event.
We pushed the button for the run, and all these dignitaries were there, and the stand blew up. I mean, not a little blow up. This was a big blow up that lit up the sky, and it was a 1,000-foot plume went up. And we all turned pale. And I could hear von Braun saying, "Oh, shit." He turned around and walked out. Well, that led to a very long but wonderful episode that had a happy ending, where that place turned to and found out why that problem happened. It was an ignition problem. And believe it or not, all previous tests, we had the RL-10 was laying horizontal, and it ignited very, very reliably. When you put it in a vertical position, you got the wrong mixture ratio for ignition. One lit, and the other one just put down into a common exhaust, unburned propellants, and it went off like a bomb. But getting to that answer was one of the most exciting technical witch hunts I've ever been through.
The RL-10's ignition problems were ultimately solved, and the engine passed its preliminary flight rating test in January 1962. The J58 passed its preliminary flight rating test just a few months later. Under a cloak of secrecy, flight testing of the A-11 progressed rapidly, and an experimental interceptor version, the YF-12A, entered operational service. A reconnaissance version became operational in January 1966, the legendary SR-71 Blackbird. Though now retired from the U.S. Air Force, the SR-71 still holds numerous speed and altitude records thanks to the J58. 2,193 miles per hour in level flight, and sustained level flight at 85,069 feet. In 1990, it flew from Los Angeles to Washington, D.C. in 1 hour, 4 minutes, and 19.89 seconds. The RL-10 was also about to make history, but not without some tense moments first.
The first launch, of course, was disastrous because the Atlas launch vehicle suffered a failure on liftoff and exploded essentially on the pad. There's a funny story about that. One of our people was in the telemetry shack at the Cape, and his job was to monitor the telemetry from the engine during the launch and report back to Bill Gorton, who was the vice president and general manager down here then, what kind of performance we were seeing from the engine once it fired in space. So the Atlas fired and lifted off about 3 feet off the pad, and the sustainer engine shut down. and the vehicle slowly settled back down into the launch pad into a tremendous explosion. You can imagine how big a fireball that much hydrogen and oxygen makes. Well, the telemetry package on the Centaur vehicle, the upper stage, which our engines were on, was battery powered, and it was external to the vehicle. And when the explosion occurred, it was blown free of the vehicle into a field about 300 yards away, and it lay there radiating. It was still sending out signals. Our fellow in the telemetry shack was watching those signals on a trace on an oscilloscope, and it didn't show anything other than that everything was normal. The engine, of course, hadn't fired at that time and wasn't supposed to, so all the traces were flat and looked normal. So he was reporting back to Bill Gorton and the rest of the management group down here that everything was fine. In the meantime, the vehicle was a smoking pile of rubbish on the launch pad.
Finally, in November 1963, two RL-10s successfully boosted a Centaur upper stage into orbit.
Again, the group of us had gone there somewhat apprehensive because we had had so many problems in the past, and this launch was picture perfect. Everything went according to schedule. And when the telemetry traces showed that the RL-10s had fired right on schedule, the chamber pressure came up and held constant, right where it was supposed to, it was the greatest feeling you can imagine.
2 months later, the 6 RL-10s of a Saturn S4 stage propelled a 37,000-pound payload into orbit, successfully demonstrating the practicality of hydrogen-oxygen fuel for the Apollo Moon exploration program. The RL-10 went on to set the standard for performance and reliability in upper-stage propulsion systems. It boosted 7 surveyor missions to the lunar surface in preparation for Apollo. It powered Mariner and Pioneer to our neighboring planets, and sent Voyager to the farthest reaches of our solar system and beyond. The success of the RL-10 and J58 quickly led to other pioneering programs. FRDC began development of a high-pressure rocket engine quite different from the RL-10. Instead of an expander cycle, the engine used a pre-burner to drive turbopumps delivering the cryogenic fuels. It had tremendous growth potential. From a 50,000-pound thrust demonstrator, the concept grew to 250,000 pounds in just a few years. In June of 1964, the FAA awarded both Pratt Whitney and General Electric contracts to develop an engine for a proposed supersonic transport. With the experience of the J58, Pratt & Whitney's designers appeared to have a substantial edge in development of this 54,000-pound thrust high-Mach power plant, and they tackled the project with enthusiasm. Employment rose to 7,000. The engine was completed ahead of schedule and ran on March 31, 1966. By December, the test phase was complete, and the engine had run at speeds up to Mach 2.7 at 65,000 feet. The Christmas holidays began on a jubilant note. On New Year's Eve, that euphoria was shattered with the announcement that GE had won the SST engine contract.
The unfortunate thing is that even though the SST program didn't proceed, GE had millions of dollars in development for high-temperature jets that we didn't get.
Other development programs, such as the C-Jet marine engine, were lacking in a viable market. In an effort to keep the facility alive, responsibility for all J58 overhaul was transferred from East Hartford to FRDC, with production and assembly of several other military engine components. In September 1967, FRDC received a contract for development of the ST-9, a new turboshaft engine for the proposed U.S. Army UTAS helicopter. The company also started contract work on a 250,000-pound thrust rocket engine and began research on the use of gas dynamic lasers as weapons systems. But none of these programs offered the immediate business benefits the company required. The future of FRDC was still in jeopardy. 1967 was a rough year for the Air Force, too. Soviets introduced the MiG-25, a formidable new fighter which shattered numerous performance records and threatened NATO air dominance. In the skies over North Vietnam, it was increasingly evident that the dogfighting capability of current U.S. fighters was marginal at best. The Air Force quickly initiated a competition for a new air superiority fighter, the FX competition. The Navy, too, was seeking a new engine for its proposed F-14. Once again, Pratt Whitney was pitted against GE. This was a must-win situation, and FRDC responded admirably. Their entry? The remarkable F-100. 1968, FRDC's 10th anniversary. 10 long years. 1 short decade. America was now deeply enmeshed in Vietnam, but results seemed frustratingly elusive. World War II had ended with a dearly bought but unequivocal victory. Korea concluded with an unsatisfactory and unsettling stalemate. With Vietnam, the public became increasingly skeptical of official reassurances. Government news releases reported a light at the end of the tunnel, but the massive communist Tet Offensive of 1968 finally shattered public complacency and polarized the nation. Ahead, the nation faced a painful extrication from Southeast Asia. There were moments of glory, though. In 1969, we watched our TVs in awe and anticipation as Neil Armstrong took that first small step and forever changed mankind's place in the universe. Our old icon, the automobile, no longer sported fins, but cars were still aerodynamic and powerful. If the events of the late 60s and early 70s left the public disillusioned with the military-industrial complex, Pratt & Whitney knew the future was not that simple. Regardless of public opinion, the nation still faced very real threats and possibilities. The F-100 competition was challenging. The Air Force demanded an engine with a higher thrust-to-weight ratio than any previously designed. Winning the contract was critical to FRDC's survival.
Well, the biggest problem in the F-100 is to get the weight down. The original design we had didn't make it. We had some pretty good information that told us we were off the mark on the weight. And Bill Brown, I will call credit for getting a design change that got the weight down. But doing this, getting the weight down is what made it risky. The other parameters were well within hand. Trying to do this job with the weight that we went after was a real tough program. And to do this, we did need to have IN-100 in the turbine discs.
Another materials laboratory breakthrough, gatorizing, provided one key to solving the weight problem.
We did a very unusual thing. And frankly, I don't remember why we did it, but we did. We took the material and we did not heat treat it, and we tested it. And we tested tensile properties up in the 1700 to 2200 degree range, and stress rupture and tensile. And we were absolutely amazed when the rupture results came in, because as soon as the guy loaded the specimen, it just stretched like chewing gum. And we became very excited over this, because these alloys like IN-100 are very difficult to move, to forge without cracking and so on. And here was this stuff just, stretching like putty. So it occurred to us, gee, if you can get the material in that kind of condition, if you can pull it like that in tensile, why can't you put it in a compression, which is a forge motion, and do the same thing and come out with forgings that are very, very close to that shape, with a reduction of machining and something that had no cracks in it. Like I said, I have a super strong alloy like IN-100. So we set up a little forging rig, put the material in a superplastic condition, heated up the whole system, and held it at temperature. And we were able to make little small pancakes with different beautiful surfaces and tight configurations. So that said to us, boy, we got something here. And we went after a big forge cycle, and then, of course, we sold it to the Air Force for F-100 disc. And In fact, we sold it to them and we won the contract before we ever made a full-scale disc. We based everything on small-scale pieces, which is kind of dangerous.
Dangerous it may have been, but the full-scale IN-100 discs proved every bit as good as the tests promised. The result was a lightweight engine with an 8-to-1 thrust-to-weight ratio, producing nearly 25,000 pounds of thrust. It was a 25% improvement over any previous engine. The first F-100 engine ran June 30th, 1969, and began a grueling test series. Problems encountered were quickly fixed, and the schedule was maintained. In March of 1970, the Air Force announced Pratt Whitney's selection to power the new F-15 Eagle. Simultaneously, the U.S. Navy selected a version of the same engine, the F-401, for the new F-14 Tomcat. Full-scale development began immediately. It was a rigorous schedule, running in parallel with airframe development. In November 1974, the first production F-15s were delivered on time to the U.S. Air Force. The Navy version of the engine, however, experienced delays. The Navy canceled its order for the F-401 and opted for East Hartford's existing TF-30. In May 1970, NASA requested design proposals from Pratt & Whitney, Rocketdyne, and Aerojet. A high-pressure, reusable, hydrogen-oxygen-powered main engine for the future space shuttle.
Dick Mulready, along with some folks from the research lab, had started a program of high-pressure, high-chamber pressure rocketry, and had demonstrated very successfully that a very high-pressure engine could be built and cooled and would be very efficient. So when the Space Shuttle main engine program came along and the request for quotation went out for the engine, we responded with a proposal based on that technology. The company had put about 10 years of effort into it and a lot of company money. It was R&D, of course, but it was still all paid for by the company, and we had actually demonstrated the concept at full price. So we submitted our proposal to NASA, and in this new environment that we were learning to live in, where a contractor is just a person that NASA uses when it's convenient for them, they gave our design, our proposal, of course, which we had written under their aegis and they had paid for, they gave that information to our competition. And they said, we like this design concept, this high-pressure engine concept, better than the concepts which you have put forward. So we want you, the competitors to Pratt & Whitney, to take their concept and make a proposal based on that. Well, that was an insult beyond insult as far as we were concerned. But it happened, and we had to live with it.
Despite this turn of events, Pratt & Whitney was confident that their experience and established technical expertise would prevail. It came as a tremendous shock when the contract was awarded to Rocketdyne in July 1971. A satisfactory explanation for the choice was never offered. Pratt & Whitney appealed the decision to the U.S. Comptroller General. After a 6-month legal battle, Pratt & Whitney lost the appeal. The decision effectively took FRDC out of the space business for years to come, except for continuing development of the workhorse RL-10. That loss, however, may have had some positive aspects.
My view is it's a doggone good thing we didn't get that competition because we were right in the middle of the F-100 program at that time. And there was absolutely no way in the world that we could have handled the two of them. They both would have failed, and we would have gone down the tubes.
In December of the same year, the U.S. Army selected GE's entry over Pratt & Whitney's ST-9 to power its new utility helicopter. On the plus side, however, in addition to the huge new F-100 contract, FRDC's laser research was generating interest. In December 1972, the Air Force funded a program to place a gas dynamic laser aboard a flying test bed, the Airborne Laser Laboratory.
The SR-71 is a combination of power and majesty. When you look at it, it just has a mystique that I think is going to live for generations and generations. I wish I could take everybody up to 85,000 feet, because you can see 350 miles in any direction. You can see the curvature of the earth, mountains, 10,000 foot mountain, flat. I can say without a question is that people knew that there'd be an SR flight, and when they cranked those engines, the Buick Wildcat would scream. Then when the SR engines came on, people from around the base would just kind of stop. 117 decibels, that's what the SR was on takeoff. Six presidents used the SR-71 extensively because they had a great sense of confidence that it can in fact go out, collect the information required, and bring it back. Hundreds of missiles were fired at this airplane. I couldn't tell you how many times fighters came up to intercept me. I remember part of our missions when I was flying in the late 70s was fly through rings of SA-5s. We knew it was a very capable missile system. They weren't concerned too much about the SR, but they were very concerned about others. And they figured we could collect enough information and we could understand how that missile system would work. If we carried the nose camera, which we called the country's camera, it took a picture 72 miles wide. In 64 minutes, you would film 100,000 square miles. The film itself was 10,500 feet long, 5 inches wide. I would say my mission into the Middle East for President Carter was one of the most interesting. It was supposed to be 3 missions, but we picked up all the targets in that first mission that they needed, so that the next 2 missions were canceled. The airplane loved to fly straight and climb and accelerate. Most of the time at altitude, 80 to 85,000 feet, it was kind of like a nice Beamer or a Cadillac. But the airplane sensitivity was on a curve like this. So the faster you went, the airplane became much more sensitive and had to be handled much more delicately. The genius of this airplane was that the faster we went, it's the only airplane in the world, we burned less fuel. The greatest sonic boom that was ever set up, it was May 1972. 3 SR-71s took off from Okinawa, Japan, and simultaneously overflew Hanoi at the same time. I've talked to the POWs. They said it scared the living daylights out of the guards because they'd never heard a shock like that. It didn't sound like a bomb, and they actually fled. We called the shock waves that came across the ground the sound of freedom. Can you imagine that sometimes we were tasked to overfly foreign ceremonies, to boom heads of state when they were greeting each other, to remind them that they were doing things that were counter to U.S. policy? I was blessed in the Air Force because I was lucky to fly a number of Lockheed products. Lockheed was always there to bring in new innovation that met our needs as warfighters so we could better do our job. You know, it's a great celebration, and in 100 years has led to new vistas that who could have predicted.
November 29th, 1963. 1 week after President Kennedy's assassination, a meeting between new President Lyndon Johnson and his National Security Council was arranged. Present was Secretary of Defense Robert McNamara, a closely trusted advisor to both Kennedy and Johnson. Also at that meeting was Secretary of State Dean Rusk, Special Assistant McGeorge Bundy, and CIA Director John McCone. The issue was the secret project currently underway at Lockheed Skunk Works. The aircraft, capable of Mach 3, an elevation of 100,000 feet, and a low radar cross-section, began during the Eisenhower era under the code name Oxcart. Giving the U.S. a huge advantage over the Soviets in aerial reconnaissance, the project was enthusiastically supported throughout the Kennedy years. The question now was, should the administration release any information about this state-of-the-art plane to the world? McNamara favored complete disclosure to the press. If information about the A-12 was revealed, it would severely weaken the case for another Mach 3 plane also being developed, the astronomically expensive B-70 Valkyrie, a bomber that was already obsolete and high on the Secretary of Defense's chopping block. Opposing the early release was McCone and Bundy. In a shrewd calculation, it was suggested that the president instead wait until closer to his re-election the following year, realizing that the plane, with all of its technological breakthroughs, could be used as political capital. It was the plan favored by Kennedy before he died, said Bundy. Johnson, after careful consideration, decided to hold off on Oxcart, or as LBJ said, keep his powder dry. In February of 1964, however, with Senator Barry Goldwater of Arizona, a top contender for the presidency, telling the American people that both the Kennedy and Johnson administrations had failed in sponsoring any new aircraft projects, LBJ decided to fire back.
One of the best-kept secrets in military history is unveiled by President Johnson at his first General News Conference since taking office just 100 days ago. His startling announcement is that after 5 years, the U.S. has developed a jet high-altitude interceptor capable of flying long distances at 2,000 miles an hour, 3 times the speed of sound.
The United States has successfully developed an advanced experimental jet aircraft, the A-11, which has been tested in sustained flight at more than 2,000 miles an hour and at altitudes in excess of 70,000 feet. The performance of the A-11 far exceeds that of any other aircraft in the world today. The development of this aircraft has been made possible by major advances in aircraft technology of great significance for both military and commercial applications. Several A-11 aircraft are now being flight tested at Edwards Air Force Base in California. The development of a supersonic commercial transport aircraft will also be greatly assisted by the lessons learned from this A-11 program. For example, one of the most important technical achievements of this project has been the mastery of the metallurgy and fabrication of titanium metal, which is required for the high temperatures experienced by aircraft traveling at more than 3 times the speed of sound. Arrangements are being made to make this and other important technical developments available under appropriate safeguards to those directly engaged in the supersonic transport program.
The result of the press conference caused the program to split into 2 different directions. The YF-12 interceptor, mistakenly called the A-11 by the president, was sent to Edwards Air Force Base as an overt program. The reconnaissance spy plane, which later became known as the world-famous SR-71, would instead remain black.
A United States Air Force Strategic Air Command weapon system. The SR-71, a highly sophisticated reconnaissance aircraft of the 60s, still ahead of the state of the art in the 70s, was first announced in February 1964. The program was started initially with a systems project office, given specialized management authority, and answering directly to Air Force headquarters. As the program progressed, the Specialized Management Authority was transferred to the present Advanced Systems Program Office with complete administrative, engineering, and logistics responsibility. A pattern now accepted for several key Department of Defense programs. The Lockheed Advanced Development Project, nicknamed the Skunk Works since the early 40s, well known for its ability to produce in a tight security atmosphere, was selected to proceed with this highly sensitive program. A global reconnaissance system that would sustain altitudes above 80,000 feet at speeds beyond 2,000 miles per hour. With the experience gained on the YF-12 interceptor program, the task of producing the SR-71 was underway. The airframe and systems design was rapidly finalized. Engineering drawing release moved into high gear. Titanium, a light, high-temperature resistant metal, was selected to endure the torturous environment of triple sonic flight. A shop workforce, already skilled in working with titanium, was expanded as production tooling and assemblies take shape. Ship number 1 moved into final assembly. Soon another milestone is reached. Maintaining tight security and under the cover of darkness, serial number 950 leaves the assembly plant. The convoy delivering the first airplane arrives at the flight test facility. This new member of the family of Blackbirds made its debut just 22 months after go-ahead. Production aircraft scheduled for evaluation soon arrived at Edwards Flight Test Center. Almost concurrently, Lockheed and Air Force flight test efforts proved the airplane and systems. The all-important day is here. An anxiously awaited member of the team arrives on base. This first Blackbird received by the 9th Strategic Reconnaissance Wing was an SR-71B, a trainer. Enthusiastic team members are on hand to congratulate the commander and welcome the star performer. The pace quickens. Additional aircraft arrive. The new birds are on a busy flying schedule. Crews are eager to take to the skies. The SR's dagger-like shape is thrust through the sky by more power than 45 diesel locomotives. During flight, the cockpit remains comfortable, while just outside, airplane skin temperatures exceed a searing 600 degrees. The men flying this phenomenal machine soon were routinely flying Mach 3 and beyond. The team, proud of their bird and the crews that fly them, established an exclusive club. At an impressive ceremony, each crew member is awarded a Mach 3 Plus pin and certificate, honoring his first flight at 2,000 miles per hour. With the Blackbird came a new era of manned flight, introducing new requirements and procedures. The wing commander and his staff, ever mindful of SAC's goal, be ready on time, at any time, in any weather, finalized the details of a unique operational plan. The combined 9th Wing organizations work out procedures for putting the SR into service. The Chief of Maintenance, working closely with his flight line and shop personnel, continuously reviews and directs the progress of the team. An intimate knowledge of the mission equipment has been developed. Preparing the aircraft for flight is becoming second nature. Specialists working around the clock improve their maintenance skills. The transition to the new technology of the titanium bird is rapidly being accomplished by an enthusiastic team. VIPs, veteran pilots in command positions with a requirement to know the Blackbird, are scheduled for accelerated training. A thorough checkout in the simulator is the last phase before flight. With a 9th Wing instructor pilot, they board the aircraft. With a push forward on the throttles, they take to the air. A memorable experience, climaxed with an impressive red carpet ceremony. They too are now members of the exclusive club. The SR's two-man crew are assigned as a team during early flight training. A picture of an SR's flight crew would be age 30 to 35, experienced in supersonic fighters, B-58s, B-52s, and high-altitude U-2s, with 2,500 to 4,000 flying hours. Proficiency milestones are rapidly being reached. Aerial refueling from a friendly tanker gives the Blackbird almost unlimited endurance. Global range training flights are now routine. Air crews working as a closely knit unit are rapidly approaching mission-ready status. Operational readiness is near, all but the final exams. To the man, the 9th Wing is ready. The inspection team arrives on base. The operational readiness inspection begins at once. During the ORI, every man, procedure, and piece of equipment is reviewed and tested. High-ranking personnel responsible for the wing deployment decision review the inspection scores. The 9th Strategic Reconnaissance Wing had passed its operational readiness inspection. A monumental leap has been accomplished. A global reconnaissance system that will sustain altitudes above 80,000 feet at speeds beyond 2,000 miles per hour, is operationally ready. The SR-71, designed and manufactured by the Lockheed Aircraft Corporation, was delivered on schedule, within budget, and has met all its performance goals. It is supported by a responsive management system. The Strategic Air Command's 9th Strategic Reconnaissance Wing has flown thousands of hours at Mach 3. They have pioneered sustained operational flight above 80,000 feet at speeds beyond 2,000 miles per hour, carrying forward the tradition of unarmed reconnaissance. Living up to their motto, peace through surveillance, by providing information for the security of the United States and the free world. The SR-71 in a single flight has flown over 15,000 miles. On one mission, it is capable of mapping a section of the world equal to a path 60 miles wide from San Francisco to New York. The incredible Blackbirds and the team that operates them are justly proud guardians of peace through surveillance.
And looking back now, I say, yeah, I knew all the time. But, you know, that would be unfair because even though I did pretty well going through the pilot training, I always thought, oh, I'm probably not going to make it. I'll probably wash out. There'll be some phase coming that it will be too hard and, you know, I won't be able to grasp it all. And because it was all pretty amazing to me. This little kid from North Dakota going off to pilot training and learning how to fly jets. So,
I first met Al in 2001 when we were working together at Lockheed Martin's Skunk Works operation in Palmdale, California. At the time, I didn't know that Al was the world speed record holder in the Blackbird. I was at home one weekend researching the Blackbird to do some artwork, and I found a photo of Al taken right after their record speed run. And so I brought the book in on Monday and showed him the photo and said, hey, how come you didn't tell me this? And he goes, well, it was just another flight. Role models to Al were people that had substance and value. They were not only his peers, but his teachers and local business owners. Al's sense of integrity came from his father. Al remembers his father as never telling a lie and not even prone to exaggeration. Al's work ethic was also strongly influenced by his father. His father owned a bakery, and Al would go into work early in the morning with his father and help bake pies before heading off to school. During the summer, when Al was a junior in high school, he had a job where he worked 6 days a week, sunrise to sunset. Saturday was a special day because they got to get off work at 6 p.m. Al's sister has always been his biggest supporter. When Al was going to college, his sister worked extra hours to help pay for his tuition. When Al was 24 years old, he was flying F-105 fighter jets in Vietnam, completing 160 combat missions. These experiences developed his leadership skills, and led to the opportunity to fly the SR-71 Blackbird.
And one of the things that I would say is everyone is good at something. I mean, everyone is.
What was unimaginable to Al as a kid, to become a pilot, was fulfilled by his willingness to dream, a strong work ethic, and unwavering integrity. It was these values that allowed Al to not only define history, but to prove to all of us that dreams can come true.
Dream. Dare to dream.
The original SR-71, from the beginning of that project to the first flight, was about 4 years. The amazing part is they did the SR-71 back in the day of slide rules and pen and paper calculations. Now with computers today, we could turn the design work much faster, and it really becomes a case more of how quick the customer says they need it. In the late 50s, when they were flying the U-2s, they were starting to recognize that the Soviet threat to those aircraft was becoming more severe, and they needed something that flew higher and faster. So it was really answering a need. Since it flew so high and so fast, the tanks got very hot, and what they discovered was conventional jet fuel was going to boil off. So they got with one of the oil companies and came up with special fuel additives, and it's a variation of jet fuel. Normal jet fuel is known as JP4. There's a special fuel called JP7. It's a little bit heavier and doesn't boil as quickly as traditional jet fuel, and it's only used for the SR-71 engine.
Of the many aircraft whose origins can be traced back to the Lockheed's renowned Skunk Works, none is more significant than the A-12. More than any other aircraft, this titanium masterpiece represented the apex of aeronautical engineering in its day, not only at Lockheed, but at every significant aerospace engineering bureau around the world. Today, over 3 decades after its first flight, it remains the aircraft by which all others are judged. Project Suntan had given Telly Johnson and the Lockheed Advanced Development Team engineers a significant opportunity to explore the attributes of hydrogen propulsion systems. Equally as important, however, Suntan also permitted the exploration of advanced airframes optimized for the first time to cruise at speeds well in excess of Mach 3. Soon after the U-2's first flight during 1955, Richard Bissell moved quickly to organize the research and development of follow-on systems, including what was to become the A-12. New studies, conducted under the codename Gusto, were initiated exploring the design and possible development of a totally new subsonic reconnaissance platform that would be designed from the start to incorporate the lowest RCS obtainable. The resulting analysis concluded that supersonic speeds, coupled with the use of radar-attenuating materials and radar-attenuating design, greatly reduced the chances of radar detection, though it did not reduce it to zero. Lockheed Aircraft Corporation and the Convair Division of General Dynamics during the fall of 1957 were to respond to a general operation requirement calling for a high-speed, high-altitude reconnaissance aircraft, but to do so without a formal contract or government funding. Johnson spent virtually every available minute working on the Advanced Aircraft Program, which he sometimes jokingly referred to as the U-3. Project Gusto was now terminated, and a new codename, Oxcart, was assigned. Ben Rich would note that the A-12 was comprised of 85% titanium and 15% composite materials. Learning to work with titanium proved to be a major undertaking. The myriad breakthroughs pioneered by Skunk Works' manufacturing team in conquering this metal were made one of the great and unheralded successes of the most incredible program. Just a great deal of work with the many problems we are trying to get this airplane built. Everywhere you turn, there is a tremendous problem requiring invention, new systems, and money, said Johnson. An official first flight, with appropriate government representatives on hand, now was made on April 30th. Nearly a year behind schedule, the aircraft became airborne for the first time. With Lou Schalk at the controls, the aircraft lifted off at 170 knots. The landing gear was retracted and climb was made to 30,000 feet. A top speed of 340 knots was reached during the flight, which lasted for 59 minutes. Following an uneventful landing, Schalk presented satisfaction with the aircraft's stability and the way it handled. On the second flight, on May 4th, the A-12 went supersonic for the first time, reaching Mach 1.1. Problems were minimal, and Johnson began to feel confident that the flight test program would progress rapidly, possibly recovering some of the time that had been lost in the drawn-out manufacturing process. The Cuban Missile Crisis now reinvigorated the program. The loss of Major Rudolph Anderson's U-2 over Cuba on October 27th underscored the increasing vulnerability of this subsonic platform when operating in denied airspace, and this was not lost on intelligence community offices involved with the overflight program. Successful execution of Oxcart now became a matter of highest national priority. At the end of 1962, 2 A-12s were in flight test, one powered by J-75s and the other powered by one J-75 and one J-58. A speed of Mach 2.16 and an altitude of 60,000 feet had been achieved. Flight test progress was still slow, and the engine delays and thrust deficiencies remained a major concern. Meanwhile, by the end of 1963, the CIA's A-12 flight test program had resulted in 573 flights totaling 765 hours. 9 aircraft were on hand at the test location. As noted earlier, during July, Mach 3 had been reached for the first time, and during November, design speed Mach 3.2 had been reached at an altitude of 78,000 feet. It should be noted that at this point, on July 24, 1964, President Johnson made the first official announcement concerning the forthcoming Lockheed SR-71. While the A-12 situation vacillated back and forth between an operational commitment and a continued wait-and-see, flight testing of the YF-12A had continued. During July of 1966, Johnson wrote in the log, "We were directed to give up further flying of the YF-12As. Although we had proposed shooting down a drone at Holloman to get the effect of ground clutter for low-altitude targets." The following August 5th, he wrote, "We have laid off half of our test crew of the YF-12A and are maintaining only people to store the airplane or send it to Burbank. We are very near the end of this program." As late as January 26, 1967, Johnson made the following comments in the A-12 log. "We jointly agreed there would be just one round and not two. That seems to have been a very accurate evaluation, as it seems that 30 SR-71s give us enough overflight reconnaissance capability and we don't need the additional 10 A-12 aircraft." On January 5, 1968, an official wire closing down the F-12B was received from the Air Force. The YF-12A program would be formally ended on February 1st. In a final disheartening move, the Air Force, on February 5th, sent Johnson a letter instructing Lockheed to destroy the A-12 F-12 tooling. The final A-12 flight took place on June 21, 1968, when the last remaining aircraft, number 131, was ferried from the test location to Palmville by CIA pilot Frank Murray and placed in storage. It would remain there for the following 2 decades. On June 24th, Johnson wrote, "While the intelligence community in Washington wanted very much to keep the A-12 program going, the present financial situation cannot stand the strain. It's a bleak end for a program that has been overall as successful as this." In summary, the A-12 program lasted just over 10 years from its inception during 1957 to its termination during 1968. The Skunk Works produced 15 A-12s and 3 YF-12As. 5 A-12s and 2 YF-12As were lost in accidents. 2 pilots were killed, and at least 6 had narrow escapes. In addition, 2 F-101 chase aircraft were lost with their Air Force pilots during the A-12 test program. The main objective of the program, to create a reconnaissance aircraft of unprecedented speed, range, and altitude, was triumphantly achieved. It may well be, however, that the most important aspects of the effort lay in its byproducts, the notable advances in aerodynamics, engine performance, cameras, electronic countermeasures, pilot-like support systems, and the arcane art of milling, machining, and shaping titanium. Altogether, it was a pioneering accomplishment almost certainly never to be repeated in the history of aviation. The YF-12A developed into the SR-71, and in that case, again, the cost performance was excellent as we gave back to the government well over $19 million on the contract, and we consider it to be a success. On December 6, 1962, Telly Johnson noted in his log, "Working on R-12 Universal Airplane, using company work order, can get no decision on any military version of the aircraft, but there does seem to be considerable interest in it." The Johnson's rationale for this design was based on the premise that if he produced a single platform capable of performing a reconnaissance, recon strike, or intercept role depending on customer needs, it would greatly simplify production, and it eliminates the necessity of the Air Force deciding which version they want to buy. 7 days later, the Skunk Works was visited by several SAC personnel, and Johnson logged that they wanted to see what kind of a reconnaissance version would meet SAC's needs. We prepared our proposal for a 140,000-pound reconnaissance airplane capable of carrying 4,300 pounds of reconnaissance gear and gave it to Colonel Templeton with a forwarding letter. By March 18, 1964, R-12 construction was moving along with considerable rapidity, but contract negotiations had yet to be concluded with the Air Force. Johnson noted in the log, spent several days on the first R-12s. It is extremely difficult to get a reasonable profit for what we do, and no credit is given for the fact that we operate more cheaply than others. All activity relating to the R-12 and RS-12 configurations had, of course, been kept completely under wraps in the Skunk Works and within two confines of the involved Air Force and CIA offices. On July 24, 1964, however, President Johnson made his memorable announcement revealing to the world the existence of Lockheed's Mach 3 capable reconnaissance aircraft. I would like to announce the successful development of a major new strategic med-aircraft system which will be employed by the Strategic Air Command. This system employs the new SR-71 aircraft and provides a long-range advanced strategic reconnaissance plane for military use, capable of worldwide reconnaissance for military operations. The Joint Chiefs of Staff, when reviewing the RS-70, emphasized the importance of the strategic reconnaissance mission. The SR-71 aircraft reconnaissance system is the most advanced in the world. The aircraft will fly at more than 3 times the speed of sound. It will operate at altitudes in excess of 80,000 feet. It will use the most advanced observation equipment of all kinds in the world. The aircraft will provide the strategic forces of the United States with an outstanding long-range reconnaissance capability. In August 1964, Kelly Johnson phoned Bob Murphy and asked him if he wanted to work on the new reconnaissance aircraft. At the time, Murphy was a superintendent in charge of D-21 drone production. He accepted the offer and was immediately briefed by Johnson, who said, "I want you to go to Palmdale and get Site 2 away from Rockwell. Hire the people you need. The pieces for the aircraft will be up with you on November 1st, and I want her flying before Christmas." The SR-71 was 107 feet 5 inches long and had a wingspan of 55 feet 7 inches and a wing area of 1,605 square feet. It stood 18 feet 6 inches high to the top of the rudders, and its gross weight varied from 135,000 pounds to over 140,000. The effect of thermodynamic heating brought about by the aircraft's extreme operating envelope was a major factor affecting its construction. Fully 93% of the airframe was built from titanium, while the remaining 7% consisted of laminates of phenylsilane, silicone asbestos, and fiberglass to help produce the aircraft's RCS. The SR-71's forward fuselage has a circular cross-section and is of semi-monocoque construction. It has the pilot and a reconnaissance systems operator, RSO, seated in tandem, the front undercarriage, fuel cells, and the air refueling receptacle. The delta wing features 2 prominent engine nacelles, each mounted at mid-semi span and blended into the wings to further reduce RCS. 2 rudders mounted on top of each nacelle and canted inboard 15 degrees from the vertical also reduce the aircraft's radial signature. A large aft-moving spike extends forward from each engine nacelle, which helped to regulate mass airflow to the 2 Pratt Whitney J58 engines. The maximum fuel load weight for the SR-71 was 8,280 pounds. And it was carried in 6 fuel tanks, built to cruise an afterburner at Mach 3.2 and at altitudes in excess of 80,000 feet. The aircraft encountered extremely high airframe temperatures generated by thermodynamic heating. This, coupled with the diverse operating envelope of its Pratt & Whitney J58 engines, required the development of a special fuel which served not only as a source of propulsive energy, but also as a hydraulic fluid optimized in the engine hydraulic system to activate the main and afterburner fuel nozzles. On the ground, the aircraft is only half filled with fuel and then pressurized using LN2 to 1.5 psi above ambient pressure. Shortly after takeoff, the SR-71 would rendezvous with a tanker and get topped off. The air inlet control system was a major innovation used to exponentially increase the speed performance of all Kelly Johnson's so-called Blackbirds. At Mach 1.4, the outlet doors located in the exterior of the engine nacelle began to modulate automatically in order to obtain a prearranged ratio between dynamic pressure outside the inlet throat and static duct pressure inside the inlet towel. At 30,000 feet, the inlet spikes unlock and, at Mach 1.6, began moving towards the rear, achieving their fully aft position at Mach 3.2, design cruise speed. Cruising covertly during operational missions at speeds in excess of a mile every 2 seconds, it was essential that the SR-71's navigation system was both highly accurate and non-reliant upon external navigation aids to ensure the aircraft remained on the black line. At the heart of successful missions accomplishment, therefore, was the Neutronics Astro Internal Navigation System, or ANS, designated NAS-142V2. Originally designed for the Douglas Skybolt air-to-surface ballistic missile, which was cancelled in 1963, it proved to be a perfect solution for navigating the SR-71 after a few modifications and updates. The system combined data from the internal navigation platform with a timed data accurate to within 5 milliseconds. Position updating was achieved automatically by astro-tracking at any one time 6 of the 52 most prominently visible stars by day or night. In effect, using nature as a global positioning system long before GPS was developed. When the autopilot was coupled to the ANS via the AutoNav function, the SR-71 could be flown automatically, adhering precisely to a predetermined flight path that was loaded pre-flight into the ANS's computer memory. To facilitate maximum mission flexibility, the SR-71 featured 3 interchangeable nose sections housing either a high-resolution side-looking radar used for brown mapping and referred to as CAPRE, standing for Capability Reconnaissance Radar, an advanced synthetic aperture radar system, or so-called glass nose, housing a palletized optical bar camera. The SR-71 did not carry any form of defensive weaponry, save that which was generated electronically. ECM was and remains a highly sensitive area, where fast-moving technological advances meant that the SR-71's defensive electronic systems required continual updating throughout its operational life. Within the SR-71's cockpit, pressurization was allowed to fall steadily as the aircraft climbed from sea level to 8,000 feet, whereupon it remained constant to 25,000 feet. This ensured that the fuselage wasn't subjected to unduly high pressure gradients, which in turn meant that the aircraft's structural weight would be reduced. However, if pressurization was lost or the crew needed to eject, survival was dependent upon each of them wearing a full pressure suit. This requirement was enforced by Air Force Regulation 60-16, which stipulated that full pressure suits must be worn when falling above 50,000 feet. In 1977, the company developed the next generation of pressure suits. Designated the S-1030 series and featured a high level of commonality between the U-2 and SR-71 programs. Colored in old gold, the suit incorporated state-of-the-art textiles and was more durable and comfortable. Its 4 principal layers consisted of outer coverall of Nomex that was durable, care and fire resistant. The helmet, designated GN121394, was attached to the suit via a roller ball ring to enable the head to be turned. Oxygen was supplied to the crew members through holes situated around the helmet face seal. An airtight port located on the lower right side of the helmet enabled crew members to drink water of the straw to ensure they remained hydrated, and a level of sustenance was also available in the form of liquidized food dispensed from a tube. Gloves completed the pressure seal and were attached via wrist hinges. Boots featured heel retraction strips that were connected by a cable to the ejection seat on entry to the cockpit. The complete pressure suit system cost about $130,000 a copy. Crews were issued with 2 and may lasted 10 to 12 years, undergoing a complete strip-down overhaul every 5 years and a thorough inspection every 90 days or 150 hours. December 22nd, the first SR-71, with Skunk Works test pilot Bob Gillen at the controls, took to the air for the first time. Departing from Lockheed's Air Force Plant 42 Site Facility 2 at Palmdale, it remained airborne for just over an hour and reached a speed in excess of 1,000 miles an hour, which, Johnson noted, is some kind of a record for a first flight. Though the SR-71's first flight had been completed with few difficulties, ongoing flight testing of the aircraft had not been comparably problem-free. The SR-71 flight test program, conducted at Palmdale, like that of its A-12 predecessor, was not without its accidents. The first, involving the third SR-71A, occurred on January 25, 1966, when Skunk Works pilot Bill Weaver miraculously escaped without losing his ejection seat. His back sealer, Jim Zwayer, was not so lucky and was killed. At the time of the accident, the aircraft was in a right turn and then right inlet forward bypass doors were being controlled manually by Weaver. Though SR-71s finally were beginning to enter the operational Air Force inventory, the miscellaneous subsystem problems remained difficult to overcome. tank sealing, and range deficiencies continued to plague the aircraft, including those considered operational at Beale Air Force Base, and corrective action was painfully slow in overcoming them. By late 1967, all 31 SR-71s on order from Lockheed had been completed and delivered. By late September of 1969, the SR-71 was well on its way to a long, illustrious operational career. SAC already had flown well over 100 hot missions out of Tadina. NASA, for the first time, formally inquired into handling an SR-71 for test purposes on December 29, 1970, when a query was received by the Skunk Works concerning possible use of the aircraft to launch test-scale models of the forthcoming space shuttle. On July 28, 1971, Johnson noted in a log, "Nothing new on the SR-71 operation. SAC made a 10-hour flight a short time ago on which about half the time was over Mach 3 and 80,000 feet. They flew 10,000 miles." The Vietnam War had successfully justified the SR-71's existence from the time of its operational debut during 1968 through 1973. Some 600 missions had been logged during the course of Vietnam operations, and the aircraft had logged an enviable record of dependability and mission success. Temporary deployment to forward operating locations worldwide were undertaken with considerable alacrity, and during the course of its service career, the aircraft overflew almost every major political and military significant hotspot in the world, gathering intelligence data of inestimable political and military value. The previously mentioned YF-12A speed and altitude records were eclipsed by the SR-71A during a series of Federation Aeronautic International monitored flights during 1976. As of writing this, all of these records still stand, including the world's absolute speed and sustained altitude records. During the late 1980s, as major international political and economic changes began to manifest themselves throughout the world, the U.S. intelligence community began to reassess priorities and, in particular, the way it was going to spend its limited financial resources. Virtually every program, including the SR-71, was reviewed with the intent of determining its long-term viability and, in particular, its simple cost-effectiveness. As a result of this review, and in light of advances in other sensor system programs, on October 1, 1989, all SR-71 activities, with the exception of crew proficiency training and associated training flights, were suspended while the Air Force awaited release of the 1990 fiscal year budget. When revealed several weeks later, funding for the SR-71 program had been eliminated. Accordingly, all Air Force SR-71 operations were terminated officially on November 22nd.
Good evening. Recent budgetary cuts for the Air Force have ended funding for the SR-71 reconnaissance aircraft program. Local civilian and military personnel had the opportunity to view the final functional check flight of the SR-71 as it prepared to return to the United States.
Rolling down Kadeena's runway for one of the last times, the SR-71, nicknamed the Habu, performed a functional check flight in preparation for its last trip to the United States and into the pages of history. The atmosphere was charged with excitement as the flight crew, Major Jim Greenwood and Captain Steve Zaviniak, were assisted into 45 pounds of pressure suit. The physiological support technicians then conducted pressure tests on each suit and again performed these tests in the aircraft during free flight. The extra tests help ensure the suits will work in the event the pilots need to eject. The suits allow ejection at altitudes above 80,000 feet at speeds of Mach 3. After all pre-flight checks were done, the engines were started and the Habu came to life and soared into the skies of Okinawa for one of the last times. From Kadena Air Base, I'm Airman Rob Ivey.
Many of the Lockheed, Air Force, and CIA personnel who had been involved in the program during the preceding 24 years were on hand to say farewell to what many viewed as the single most significant military aircraft of the post-World War II period.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking. dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunk Works Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.